Chapter 9, we're going to start looking at more detailed analysis, more use of some of our mathematical relationships like simultaneous equations and something called the determinant and matrix. So we're going to look at branch, mesh, and node analysis. Okay, so these are all going to be probably new things to you and looking at advanced methods for doing circuit analysis. So we're going to use the branch current method to find unknown quantities in a circuit. We're going to use determinants to solve for simultaneous equations. There's some examples in here of using a calculator to solve simultaneous equations for unknown quantities. We're going to use mesh analysis to find unknown quantities in a circuit, and then finally node analysis to find unknown quantities in a circuit. So we're going to learn to use some loop analysis, understanding what a loop is, a node, a branch, and again the determinant. So in using simultaneous equations in circuit analysis, the circuit analysis methods then covered here will allow you to find two or more unknown currents or voltages by solving simultaneous equations. And you should have had some experience by now using simultaneous equations. In your math classes, you've probably solved for unknowns using simultaneous equations. These analysis methods, which include branch current, loop current, and node voltage methods, result in a number of equations equal to the number of unknowns. Okay, coverage is limited to equations with two unknowns, which is a second order equation, and equations with three unknowns, which is a third order equation. So the equations can be then solved simultaneously for the unknown quantities using one of the methods covered in this circuit. So looking at simultaneous equations, it consists of a set of n equations containing n unknowns, where n is the number with a value of 2 or more. The number of equations in the set must equal the number of unknowns. For example, to solve for two unknown variables, you must have two equations. To solve for three unknowns, you must have three equations. So the standard form of the equations, an equation with two variables, is called a second order equation. In circuit analysis, the variables can represent unknowns such as current or voltage. In order to solve for the variables x sub 1 and x sub 2, there must be a set of two equations containing those variables expressed in standard form. So what you see in the middle of the page here is actually the standard form. In the standard form, the x1 variables are in the first position of each equation. The x2 variables are in the second position of the equation. So there's your x1, there's your x2. You'll notice these numbers, we'll get to those 1, 1, 1, 2, 2, 1, 2, 2 later as we progress. The variables with their coefficients are on the left side of the equation, and the constants are on the right side of the equation. So all of the A1 terms that have our unknowns are on the left, all of the constants are on the right. So the set of two simultaneous second order equations written in standard form is as you see it. In these simultaneous equations, the A is the coefficient of the variables x1 and x2 and can represent values of circuit components such as resistors. Notice that the subscripts of the coefficients contain two numbers. For example, A11 appears in the first equation as the coefficient of x1, and A21 appears in the second equation as the coefficient of x1. The B is the constant and can represent a source value. This notation will be useful when you use a calculator to solve equations, especially if you've got a programmable calculator. If you like doing things in Excel, Excel is an excellent tool for solving these types of relationships because you can create arrays and set up solutions from those arrays. So, in an example here, assume the following two equations describe a particular circuit with two unknown currents, I1 and I2. The coefficients are resistance values and the constants are voltages in the circuit. Write the equations in standard form. So, as we write this, we have 2 times I1 is equal to 8 minus 5 times I2, and then 4 times I2 minus 5 times I1 plus 6 equals 0. So they've written them in two different variations of ways here, okay, by using the 0 term. So what we need to do is we need to make one look like the other here. So we're going to rearrange the equations in standard form as follows. So the first one, 2 times current I1 plus, when we move the 5 I2 to the other side of the equation, plus 5 times I2 equals 8 in this case. Okay, so all we had to do was move the one term. In the second one then, we have 5 times I1, notice we're aligning these up, plus 4 times I2, these are aligned up, is equal to minus 6 when we move the 6 to the right side of the equation. So now we need to convert these two equations into standard form. Okay, so that was our task in getting this set up. If you want to do a little more work, try the related problem. In a third order equation, you'll notice now it has 3 variables associated. So we have 3 A terms in the relationship. Just as in second order equations, each variable has a coefficient. In order to solve for the variables x sub 1, x sub 2, and x sub 3, there must be a set of 3 simultaneous equations containing those variables. The general form for the 3 simultaneous third order equations written in standard form then is this. So it looks just like the previous one, but there's one more array here, one more column, if you will. Okay, we're going to start to look at these as rows and columns. Okay, so an example. Assume the following 3 equations describe a particular circuit with 3 unknown currents, I sub 1, I sub 2, and I sub 3. The coefficients are resistance values and the constants are known values in the circuit. Write the equations in standard form. Okay, so you can see all 3 of the relationships are here. We need to start moving things around because we need to set up column 1 with all the x sub 1s, column 2 with all the x sub 2s, column 3 with all the x sub 3s, and then our B column, which becomes our constants. So we're going to take each one of these relationships and we're going to start moving it around. So on the first one, we need to move the 7 to the first row or the first column. 7 times I sub 1. 2 times I sub 2 is in the right position. 4 times I sub 3 needs to be moved to column 3. And the constant here is 0, so that gets to stay. On the next relationship, though, we need to get rid of that 0, okay, because we've got 4 terms here, okay, or 5 terms here. So we need to get rid of that 0. So what do we need to do? Well, we need to set it up so that the 7 is in the constant column by itself. So we have 5 times I sub 1, that was good. 6 times I sub 2, that was good. And 9 times I sub 3 is good. In the last one, then we need to move everything on the right to the left and everything on the left to the right. And that's what we did here. Everything was pretty much aligned. So we've got row 1, row 2, row 3, row 1, row 2, row 3, column 1, column 2, column 3, and then the column in the constants. So third order equations with 3 simultaneous third order equations. So the first thing that we can look at here is doing this by substitution. And this is probably the method that you are most familiar with. So when we come back, let's start with solving simultaneous equations by using substitution.